Welcome to today's Sendo Reliability webinar. This is Fred Schenkelberg. And I was just thinking just before we're hitting record there is that the first time I learned about derating was at Hewlett Packard, and I was working. And I had taken electrical engineering in college. I had a undergraduate degree and a bachelor's in electrical engineering. And I do not recall if we talked about, or I don't remember doing it in the designs I did, doing derating. And at Hewlett Packard, it was a pretty formalized and widespread use of a formal system of doing derating that was pretty effective. And then shortly after that, I started teaching about derating and was building on what Dick Moss had created and was teaching across the company. And ran into lots and lots of discussions and trade-offs and issues and stuff like that concerning derating. And so it's been my history was really out of HP. And then over the years, worked with lots of other clients and helping them understand that, yeah, you really do need to create some margin here. We'll talk about that. Now, the idea is very similar to mechanical engineers, which at the time when I was teaching a lot of these classes, I also did, besides derating, I did a stress strength course or class or session in a DFR class. And the mechanical folks were very familiar with stress strength. It was taught to them. They practiced it on a routine basis. It was part of their design process inherently. And we also at Hewlett Packard tried to make that a bit more formal, but it was a pretty easy sell to the mechanicals. Whereas the electrical folks, especially new ones, had to get up to speed. And it's not a difficult thing. It's very similar to stress strength calculations. Yet electrical engineers were typically not taught that. And so it was the rare folks that knew it. And one of the issues is different companies use different programs in ways of applying it. And so we'd have more arguments about how to do derating in the company, which is not a bad problem to have rather than doing it. But the basic idea is to make sure that your components within your system each have a margin for selective stresses that are related to that component, and things like temperature, voltage, power. Let's see, there's a couple others. I'm drawing a blank. But the idea is that if your product has no margin, then transients or anomalies or perturbations or shocks to the system of some sort, say a voltage transient comes through, has a higher chance of destroying a component. And while you might get lucky and that component is irrelevant to the functioning of your product, Murphy's law says that it won't be, and it'll be the part that is critical to the functioning, and it'll destroy that part. And so we're going to talk about derating a little bit, and then how to do it, a couple different ways to go about doing it. So as is my common practice, in your organization, I find that the reliability folks have a vested interest in promoting and encouraging the use of derating in practice. Now, it doesn't have to be our job, yet it has a correlation to how well your products perform in the field. It extends their life. It makes them more robust. And it's usually pretty darn easy to do. So in your organization, do your electrical engineers, as they design and update and refine products, do they have a derating practice? Do they do this? All right, Kenneth, good. And if you don't know, you should probably find out, because it's one of the things we found when I was at HP, what Dick Moss had done is he did a survey, thank Manjo, Manja, Sebastian. Yeah, they learned the hard way. Um, what Dick Mouse had done in the 70s, that they did a survey across the various product divisions. And one of the questions is, do you do derating, and how do you do it? And they found a very striking correlation between the lower warranty costs was correlated to the formality and consistency of the derating practice. So if they used the particular method and routinely used it and double checked it, they tended to have a very low warranty. And so it was one of the top techniques or tools for design for reliability taught all the way through the corporation. And when I came along, it was by 15 years after that survey was done. And I did a similar survey and found that just about everybody, every product line, with rare exception, did derating and did it fairly well. And so there was hard to create a correlation because there was like one or two teams that didn't, and they had poor warranty. There could have been lots of other reasons for that, but I basically had a big blob of, a lot of people do it, and it's hard to draw a conclusion of that. Yet warranty over those period of time was consistently pretty low, and so that was a pretty good thing to do. So for the ones that are doing it, that's great. Hard learning it the hard way, Sebastian, is a one of my favorite lines, which I don't try to repeat with my clients or teams I'm working with, is that you should never let a good disaster go to waste. So if you have a big field problem or you have something else, is that coming in with an idea or suggestions of how to avoid that in the future is usually a good practice. Strike while the iron is hot, yet you have to, never waste a good crisis. Perfect. But you got to be careful. You can't say, I told you so. I found that out the hard way, is that, you warn them about doing derating and then they have a disaster, and then telling them I told you so doesn't get too much traction. So I avoid doing that. So it looked like, the folks that chimed in here, they do it. Yeah. And there's always issues with it. But the basic idea of derating is to avoid failures. And the issue is that we need to understand the failures. And so derating guidelines and tables and data sheets and stuff like that tend not to tell us what failures mechanisms are at play. So if you open a standard, it says capacitor should be derated 50% for voltage. Okay, why? And so I'm going to go through the process that I taught when I was at HP, and this is the way I got introduced to what derating is. And it really starts, as many of you know, I often say, is you need to understand the failure mechanisms in your components and your products and your systems and so on, in order to design away from them, to take steps to avoid them, to monitor processes to mitigate those things, and so on and so on. So understanding your failures mechanisms is a part of derating. It's the same with stress strength calculations. We'll talk some more about that in a minute. All right, so let me see if I can get this system to let me draw a little bit here. And this is going to be, yeah, I want that one. All right. And we'll go with a red. So I'm going to try to draw, an electrolytic capacitor. And many of you seen these on boards. They're usually a little bit larger style of component for most products. They're not necessarily inside cell phones and handhelds and stuff because they take space. And those systems don't tend to need a lot of capacitance. Yet in inverters and larger products and systems with higher power, we tend to need some capacitors of some sort. And electrolytic capacitors are a common component that we use in a good number of systems. And it's a can. And inside that can is a set of coiled up aluminum foil, dielectric or separator of some sort. And usually there's two separate foils and they're wound together, kind of like you lay one slice on top of the other slice. I'm waving my hands here like you can see it. And you roll it up and you put it in the can, and it has the leads come out that are attached to these two pieces of foil. And in between the foils is an electrolytic solution. And it's a little more complicated than that, but not by much. Sometimes they have separators and some other, and the particular electrolytic solution is geared and designed to help the system itself create the capacitance that it has. And so that's one way to think of it. So that's how they're built. But where does the capacitance actually come from? Let's take a look at that. Let's see if I can get this to go forward here. There we go. So what happens inside the system is that, I'll stay with red here, is that, let's say this is one piece of foil and this is one piece of foil. We're just looking on them on edge. So think of it as that this is a long strip that then is rolled up, and this is a long strip. Well, between those two, there's a space, and some designs will use some material to create a spacer there, because the space and capacitance between two parallel plates is part of what makes it a capacitor. But what the electrolytic capacitors do is they put a fluid in there, and it's a specially formulated fluid, and I'll just draw a square here for it to represent it. And it basically coats this aluminum foil and saturates it, and it lives between the foils. Now, once you apply voltage to it, right? Let's put some voltage on this, and this is the plus side and the minus side. And if I remember my notes right, that's the direction it goes. And we'll use orange to do this aluminum oxide, and it creates a coating on the I believe it's the anode side, I may be wrong, of the foil. And it's that aluminum oxide that creates a barrier to the electrons from passing through. And that in the space create, under the controlled chemistry that's occurring in the controlled application of voltage, it creates a aluminum oxide barrier or layer. And aluminum oxide, if you've ever seen a white powder on a piece of aluminum, or corrosion on a piece of iron or stuff like that, it is a flaky, fragile substance, and it's very thin. But that's the heart of this system. It's somebody a long time ago figured out how to do this and create it. And now we make millions a day, I think, in overall systems. So let's take a look what goes wrong. What is it that we derate for? Let's see if I can get this. Oops, let me get in here. There we go. What happens is, as you get voltage spikes or transients or even normal use, let's say the circuit powers on and you get a wave of voltage that goes from 0 to some value, oftentimes it overshoots. So if you were expecting it to be only 5 volts, in the initial power up, unless you do very specific things in the circuit to minimize it, it'll overshoot. It might go to 7, 8, 9 volts. And then it quickly tapers off and balances out where it should be. And in normal operation, these capacitors may see variations in the voltage that they experience across their leads. Now, internally, what is happening, let's see, change the color here. Let's do black or gray, whatever this is. It chips away at the aluminum oxide and it creates areas where it's a little bit thinner. And so the dielectric is thinner there and weaker. And so that current and voltage can more easily penetrate it. Now, one of the great things about electrolytic capacitors is that they normally repair themselves in normal operation as they're used and powered cycled and capacitance is dissipated and so on. The aluminum oxide repopulates. And so under normal operation with normal amount of voltages that's well within the range of the capacitor's design, it's usually not a big deal. Capacitors will last many years. It's when they get these transients and these other things that starts chipping away at it and starts breaking through. And at some point, it's going to see a voltage that is, say, 20 volts for a 5-volt normal circuit, and it punches through. And it's a mechanism called dielectric breakdown, and it creates a short. Now, capacitors, by their electronics behavior, is supposed to be an open. It controls the capacitance or the voltage that is allowed to move across this thing. It holds voltages and doesn't allow current to go through it. But once you punch a hole through it, now it's no longer a capacitor. It's just a short. It's just a piece of wire. And that generally is not what we want our capacitors to do. And so what we do is we say, well, if we expect, 10, say to 20 volt spikes in our circuit, then we need a capacitor that's rated, say, for 40 volts so that it has plenty of margin over the normal operating and expected transients and voltage spikes and behaviors that it would normally see. Now, understanding the failure mechanism is a key piece to really understanding and building a meaningful dialect or a derating program. But we often take shortcuts, Yeah. 100, it's the Ken is talking about it. 105C rated electrolytic caps have about double the life of 85C. Right. And temperature is one of the things that affects electrolytic caps because it tends to increase the rate of dissipation or evaporation or degradation of the electrolytic solutions that are in it. It dries out the fluid. So the higher temperature you have, the higher the diffusion rate is of this stuff being lost. And so if we run them at lower temperatures, they last longer. If we run them at lower voltages, they last longer. Now, that's the basic principle of it. So let me see if I can clear all this because otherwise follow us along. But the idea is if you understand the failure mechanism and how it behaves with different stresses, then you can say, oh, if we cut it in half or by 80% or cut it to 60%, we get X amount of reduced failure rate or X amount of increased life. It generally takes some fundamental understanding in order to create those tables and information. And in explaining, I found that knowing those mechanisms for as many components as you can sort out and track down is a solid argument to designers and engineers and especially procurement engineers as to why we need to do this. And here's the physics or science or chemistry behind why we do this. And then there's a business case to be made. If we cut the failure rate in half, we have happier customers and lower warranty expenses. So usually it makes a pretty convincing argument. But I don't even know. When I look at a derating table, it's temperature, it's power, it's one of the things with capacitors is, I'm drawing a blank on the name of it. I want to say ringing, but that's not it. Where you get kind of a chatter on the voltage line. and it degrades it. Yeah, there's noise. That's not quite a ripple current. Yeah, it's a current thing. Thanks, Mahindra. Um, and temperature. And there's a handful for each component. There's variations of what stresses are typically derated, and each one has a story as to what is that mechanism, similar to what I just went through for the dielectric breakdown. Now, if you look at a table, I think one of the things I love about electrical engineering is that there's about 25 components. There's ASICs and silicon devices and capacitors, resistors, and so on. And there's only so many technologies of each of those that we know a lot about these things, and we tend not to spend a whole lot of effort and time understanding them in great detail until, like Kenneth, you were talking or saw mentioned earlier, is you learn the hard way, and then you got to go figure it out. But the idea is that we, as reliability engineers, can leverage our knowledge of that failure mechanisms and its relationship to why we do derating to make the argument that's why we do it. Here's the background information for it. I'm not going to go into every one of these things, and I, for one, really don't know the story behind every one of the mechanisms that we're guarding against with derating. And I suspect they are out there. Now, the basic idea of derating is like stress strength. And I'll go through this quickly because I believe most of you are those smart, shiny students that know this stuff already. But let's say we go out and measure a bunch of circuits, and we measure in them in use and operating. We put some probes on our system and measure the voltage that a particular capacitor is seeing. And we'll get, what Chris Jackson would do is the random hand of chance will drop down some kind of curve. Now, it may be normal, it may not be, but it starts at zero when we have no voltage on the system at all. And we may have some small probability of high voltage spikes of some sort. And so that's the strength part of our curve. Let's use a nice blue color. And then we go measure how strong our capacitors are. So we step up the voltage until we force the capacitor to fail. Now, every capacitor is a little bit different, and they will fail with different stresses on them. And then we get another curve. And so we got a strength and a stress, two sets of curves. And if these curves are overlapping, that's the area where there's a probability that a weaker end of the strength of our capacitors meets a transient that's high enough to punch through and cause that dielectric breakdown. Or what also happens is, as our systems, for some failure mechanisms, just go through normal operation, this curve starts degrading. It moves further to the left, getting closer to where it can be overstressed and fail. Then we also have those creative customers that tend to use their system in a unusual or stressful way, and so those particular units, they move further to the right, getting closer to reducing the margin. And it's this margin was what we want, and we want it to be economically as far away as we can. And there's also the caveat that if you derate a capacitor too much, it doesn't function very well. It's a huge chunk of capacitance where we don't really need it, and it doesn't behave like we want it to. So each component has trade-offs and measures and stuff and optimum points and variations, and then you can only get them in certain values unless you're doing really customized ones. But the idea is this margin. That's what we want. We want some separation, that we select and use components that are going to meet the expected range of stresses that it's going to see. It's really a simple concept. Let's see, yeah. Now, how do we increase the margin? Derating is a preemptive one, right? Where we say, I have a 5 volt circuit and the capacitors are going to see 5 to 10 volts. So I'm going to pick a capacitor that with a 50% derating is one of the common ways it's expressed, will have a rated value, say 20 volts. And we'll just, or it could even be a 10 volt one, or like one of the comments Kenneth was talking about, temperature. If we expect our unit to be operating, say, at 40 to 50 degrees Celsius, we choose a capacitor that's rated for a much higher temperature, and it gives it margin. So that's one, is we just select stronger components. And then then the more sophisticated folks then consider, how does that capacitor degrade with time given its failure mechanisms that they're dealing with? And some derating guidelines take that into account. So it might seem excessive at the start, yet it's accounting for the normal operation degradation of your system so that it's more susceptible to failure. The hard part is is controlling the, I'm going to use orange color here, is the strain or the stress side of this thing. Now, some systems, let's say for temperature, will add cooling or heat spreaders or liquid cooling on some components or fans or stuff like that. And what we're effectively trying to do is shift the stress that our system sees under operation lower. So instead of a curve like that, we might get a curve like this, and that effectively increases the margin. So it's a way to go about doing it. We don't always win with that, and it's expensive. The other one, like for voltage transients and things like that, is that we can add circuitry to minimize transients and design circuits so that the inrush current, for example, is minimized or dampened so that it doesn't see a big inrush current. And so our current derating can be reduced. We can use the lower current rated components because we've actively designed out the stresses that they were going to see. Right? So we can do stuff to the stress side, and we often do, yet it adds trade-offs, it adds more components, it adds more complexity to our system. If we can get away without fans and without extra circuitry to dampen inrush current, for example, and we can select components that are economical for us to get that have enough margin to meet our needs, we can go with that. In some cases, you may hear this idea of uprating. Well, that just means that the stress is close to where our rated values are. And so we're hoping, and it might use a variety of different ways to mitigate the stress that's being seen. Yet the idea is that, yeah, capacitor will still work, say at 105 degrees or 120 degrees. It just won't work as long. Now, if it's in a relatively benign environment, it may last longer if temperature is the only thing increased, yet it will fail sooner than otherwise. Yet in some applications and in some circumstances, we do need to use our components at beyond their rated value. And in that area, you need to think it through and study it and do the research to get it right. So there's a handful of ways to think about this, but the underlying concept of derating is that we get a margin for specific failure mechanisms. Let's see, I think I need to erase my drawings and get rid of this table here. And then I think I can go to the next one. So why do we do that? What's the benefit of this? And I have a couple of illustrations or stories about this. The number one thing I find what happens is if you say to your development team is, here's a guideline or here's a set of rules that we're going to use for derating. When everything works, 99% of the components are easy to source and design in, and the circuit will work fine using the guidelines, so like 50% derating for voltage on a capacitor. Once in a while, because of design trade-offs, because of circuit functionality, because of space or whatever, we need to violate, and I'm using that word deliberately, the guidelines, the rules that we typically design to. And at that point, it's time to talk about it. What is the trade-off? Is it worth the trade-off of increasing the probability of failure for this component for this application? What are the risks that we're taking? And in some cases, it may well be worth it. Let's say it's as part of a circuit that is only used during uh, trading or self-diagnostics of some sort, and it's used rarely. So most of the time, that circuit will be benign. And if it doesn't work, our ability to interrogate the circuit board is reduced, yet it still functions for the customer's primary purposes. So that may mitigate the risks, and we could use a less derated component in those circumstances. And like I said earlier, is it's one of those things that if we're going to deliberately go over stress, then it's worth the discussion. It's a way to prompt that that element of the design system so that you actively think about and work with your team to consider the trade-offs and the risks involved. And is it something worth doing? But in general, derating in any of its forms, it just makes a more robust design. And that inherently then improves the reliability. Now, one of the stories I heard from Dick Moss, and this was back when I was at HP, and it was when he was done the survey and was going around the corporation teaching design teams about design for reliability. And this was in the 70s and 80, I should say the 80s, 70s and 80s. And one of the things he did is he was teaching a class in a division, and he had all the engineers in the room, and there was some senior engineers sitting in the back. And one gentleman sitting in the back with white hair hadn't really said much of anything, and everybody else was taking notes and following along with the course. And then when Dick Moss got to the part about derating and how it works and stuff like that, he mentioned to the room, that is a good idea. That's all he said. And Dick Moss later figured out that that was one of the senior design engineers and senior, like a fellow type guy within that group, highly respected, all that kind of good stuff. Well, what turned out happening is Dick Moss also had at that time access to the warranty costs for the different divisions and stuff. And he was tracking that to see if there was a benefit to reducing warranty through these design for reliability courses. Well, it turned out in about 6 months to a year, that particular division that he was teaching at dramatically reduced their warranty. I mean, cut it in half. It was already pretty low, but they cut it in half within a year. And their products were typically ones that were in customers' hands for 10 to 15 years. And it wasn't a huge volume type product line. And they continued to drop their warranty. And so he called them up and went back to them and wanted to find out, what did they do? Well, the only thing they took out of the design for reliability course, except for a few other minor little steps that they weren't doing and started thinking about, is that they actively redesigned every single circuit board meeting the HP standard for derating. And sometimes they had to completely redesign the boards because there were enough components that were different sizes, and some of the circuitry had to be accommodate the different kinds of components that were meeting the derating guidelines. And so they only shipped, I don't know, a couple of hundred units. But any of the repairs they did, they put in the upgraded boards. Any of the servicing they did, they put in upgraded boards. They redesigned every single board in their portfolio. And then over the span of about 3 or 4 years, had replaced just about all of them. And once they found the benefit of it, they actively solicited customers to allow them to upgrade their systems. And it was a dramatic example of one technique being applied aggressively, really making a difference. It more than paid for the cost of the redesign and more than the cost of all the extra more expensive components and so on. And so what we didn't know was how bad the designs were prior, although they weren't bad at all. There is a test and measurement system that had a very low failure rate in the field. It was loved by their customers and people buying their systems as being a very robust system to start with. Yet just applying it rigorously made a dramatic difference in at least one case. And I've seen it happen in other organizations where they start paying attention to it and they see results fairly quickly. And quickly, within 6 months to a year for reliability, is usually pretty darn good. So there's plenty of stories about how beneficial it is. And if the simple calculation, if you cut the failure rate for your system down, and then you look at, well, what is your existing field failure rate and what does it cost you per failure? You can quickly put a number on what's the benefit of doing this and apply it and so on. So my next step is, well, how do you apply this stuff? How do you do this? And there's a couple of options. So any comments? And a good number of people mentioned that they do derating in their organization. How do you do it? What kind of system do you have? This might be a little more than a quick answer, but I forgot to get myself a glass of water. Carl's got a definition out there. It's operating system below its headline. Yeah. Electronically, it means, if I have a capacitor, it's rated for 10 volts, I don't run it at 10 volts. Even though you could, it's rated for that. We run it less than that in order to minimize the failure. One of the things I find with vendors is they'll say this is rated to this part of it. It means that it will work. It won't immediately disassemble or fail or whatever. But it doesn't tell you how long it'll work at that level, because they don't also tell you what the expected failure rate is in a meaningful way. They might give you a fit rate, which I find to be pretty much in. So we have guideline for each type of component. Good. We follow the customized version of the IPC 9592. Good. There's also and I think I have a slide that lists the variety of different standards that are out there, and they apply to different kinds of environments or standards. And okay, Carl's got a longer comment there. I'll let you read that. The idea is that there is a range of ways to do this. So let me go through a couple of the methods that are common out there. The most common, the one I see, and I've done close to 200 different assessments of organizations. I always ask the electrical engineering teams about derating. The most common by far is, well, we leave it to engineer's judgment. Sometimes they use the data sheet. Here's one listed here that shows a derating guideline on some component. I think it's a capacitor, or some, I don't know. Yeah, I think it's a capacitor. And it gives recommendations, and it gives you a couple of things that if it's up to this temperature, use this. If it's above that temperature, here's a formula to account for it. Or just as another step. They're usually pretty simple. And like I mentioned earlier, is the hard part is the rating so that it works once for a day, for a week? Is the rating value they're giving so that it will have a very low failure rate for 20 years? And what I'm talking to vendors is no. Usually it means that you could run it at this level, but the probability of failure in a relatively short time is high. And so, but there isn't a standard for how you set the ratings on a data sheet. I think people have tried and just have not come to a common ground on it. And it's really varies by the technology, the processing being used, the technology and the process that that component experiences, and what that vendor suspects their product is being used for. And many times they just don't know. So it's a starting point when you got nothing else. But it's the data sheet and vendor recommendations is about like engineer's judgment. Well, I'll derate this because I think it's a good idea, or I won't because I want the cheaper part. If you're really looking at cost as your primary motivation, and warranty is not a consideration in that calculation, many people will use the cheapest part they can find that meets the rating and go right up against the 100% rating. And that's dangerous. Yeah. The supplier's life test is always worth pushing back on, right? So you do, you see lots of them where they do a whole pile of components and they put them in different in a temperature test, or a certain circumstance for 1,000 hours at 85C. Okay, what's the acceleration factor? What does that mean in my environment? How do I interpret that so that it's different than, oh, it survives for 1,000 hours at 85C? Well, we don't happen to be using these components for at 85C for only 1,000 hours. We might be using them for 100,000 hours. How do I judge that standard test out to time? What's the acceleration factor? What failure mechanisms is it related to, and so on? And so the idea is, yeah, they might run a standard test to say it's a life test, yet the standard itself and most vendors do not interpret that as to what does it really mean in my environment, my application. Yeah, you not only need the correct activation energy, you need to know whether you need activation energy at all. Is it a chemical process that's degrading or causing your product to fail? It may or may not be, but it's, so you got to be very, very careful with vendor standards based life tests, because unless you're really building a product that's only going to run for 1,000 hours at 85C, the test is really hard to interpret. Whether does that mean anything for your 5-year product at 40C? And activation may or may not be relevant. What if it's thermal cycling? What if it's voltage experience, the power, the distribution of power that this thing sees, and types of power events that occur, and so on. So the least rigorous, the most common is just leave it up to the engineers. And what I have found is that each engineer, depending on their background and how many lessons learned they've had in the past, the more experienced engineers tend to derate just habitually, where the younger engineers had never heard of this and it's not brought up in design reviews or it talked about in the organization. So they say, oh, it's a 5-volt rail, let's put a 5-volt rated capacitor on it, we're good. And nobody questions it. It's just their design is just thrown together and nobody checks it and nobody thinks about derating in a conscious way. And that's typically what I see in organizations I've worked with. They're self-selecting, they're ones that are having trouble. And so it's not always related to derating, yet it's an area for them to make a significant improvement, which they like, and I like it because then they pay my bill. The other one, and a couple of you mentioned this, is using a table. And the military has had tables, Intel's had table, HP has a set of tables and guidelines. What we did with our derating guideline is we pulled together folks from across different product lines and senior engineers, and not only did we create, tailor or set up the severe or benign stepping, derating guidelines. Basically, we're going to derate DC voltage by 60% for severe environments and benign environments by 90%, and so on. And it is a typical type of way these are done. Some are more complicated, some have more steps, and so on, different circumstances. But what we did is we said, what are the hints and tips? What are the things you've learned over the years that when you're selecting a capacitor, what should you or should you not do in order to create a robust product? And so people would talk about, when it would be appropriate to use an electrolytic capacitor versus a trimmer capacitor, for example, or a solid state, a film capacitor of some sort. And it became a collection of the wisdom across the organization. And so it was a table of guidelines that many of these standards documents provide, but it also provided a set of the hard lessons learned that we picked up from the organization. So we tailored that and got it condensed so that it was a pretty easy short list from each one of these things, and created a guideline plus background to the things. And then one of the things in hindsight we didn't do is list what was the failure mechanism, and where's some more information on that. And we probably could have, we didn't think of it at the time. These are good, if you're going to space, you're doing commercial. Years and years ago, I had an intern for the summer, and her task was to take a look at derating guidelines and then take a look at, what was the appropriate stuff to use for our different product lines. So we had consumer products, we had commercial products, we had test and measurement products, we had medical devices at the time in HP. And so do we need separate guidelines for those? And what we found, or what she found, was that Intel's and HP's and Dell's, we had access to all of those, plus the MIL standards, plus the space one from JPL, were all relatively similar. They were minor changes that might, instead of 60%, it might have been 65% derating, for example. They were usually within 5% of the derating recommendations for any given circumstance or period. And so she went through the derating guidelines and tallied up, was looking for differences, but we found that they're all pretty darn similar. And so pick one that you have access to, that you have some sense that working with your senior electrical engineers that are relevant for your particular one to help with the buy-in, and then use them. And use those and check them in design reviews and make it part of the normal upbringing of your junior engineers. This is the guideline we use. Now, you're successful when that guideline is stapled to the wall of the designer's space. I haven't kept track, but I suspect that the electrical engineering tools and various modeling and simulation tools probably have a way to build in your derating guidelines. I don't know if any of them do that yet or not. It wouldn't be difficult that if you have a 5-volt circuit and you're picking a capacitor, it'll flag it saying you really need a 10-volt capacitor here or better. It could automate it, but I have no idea if that's been done yet or not. But the idea is that these are just tables saying, if you have a capacitor, derate it by 90% for this environment. And by 90% means if it's a 10-volt capacitor, it would be on a 9-volt line is what you expect. So it's not a whole lot of derating. And some components are, have different recommendations, like 50% and so on. Now, another way, and Carl, I saw your comment on useful life of equipment. That goes beyond electrical derating. And so I'll come back to that if we have some time later. Well, I should say that it has some relationship to it, but it's not usually not just the electronics. It's all the other parts of your systems. I'm thinking of like a car or a motor. Um, the derating or the stress strength calculations all matter in those things. But the idea is that an asset life table uh, makes a lot of assumptions about how long they will last, if they're installed correctly, if they're operated well, if they're not seeing any flooding or adverse environmental conditions or excessive vibration, they're maintained properly, all those kinds of things. If you take care of your equipment, it'll last as long as it's expected to last and maybe longer. If you don't take care of your equipment, it's not. And by comparison, at a smaller scale, it's the same with the components on your electronics boards. Is if they're designed well, installed well, and treated well throughout their life, they will last as long as they're expected to last, and maybe longer. But if you abuse them, if they get a lot of electrostatic discharge, if they get a lot of stray radiation exposure, kinds of other factors they're not maintained or kept clean, then they won't last near as long as go. So there's so many variables in that I use asset life tables or even component life tables as, if everything's going well, we might do that. We should be able to do that. Yeah, you got to pay attention to the details. Now, this is a table out of one of the HP derating pages or derating guidelines, and it lists different kinds of technologies: the aluminum electric capacitors, ceramic capacitors, plastic and trimmer capacitors, and so on. And each technology, and this is 25 years ago, responded to voltage in a different way. Some were very sensitive to changes in voltage, say the plastic and trimmer and ceramic ones. They had a much steeper curve. Whereas a variation in voltage for aluminum electric was less pronounced, less dramatic change for it. Now, with some components and some, like resistors and some of the very basic components, their response to temperature or to voltage or power or whatever was just pretty much a flat line. You could pick whatever derating you wanted. It's really not going to make much difference. And so you pick the one that's economical. And the idea is that by understanding how that failure mechanisms responds to that stress, you get these curves. And these curves then allow you to say, I need to stay at 50% or less, or whatever the guideline is for that particular component. Because if I go above the recommended derating, it may double very quickly. Say if I go 50 to 60% derating, because that's economical or it fits the space or whatever, it'll almost double the failure rate. And that's where the discussion starts. Is it worth increasing the probability of failure for this particular component in this particular circuit and product? And if it is, then go for it. And what we did as a guideline, we said, do not exceed. It said it increases the failure rate that is just a red line that we don't want to cross. And we made those recommendations. Other teams do it in different ways. But the idea is that the curve provides you a bit of information that you can do some calculations saying, well, if I derate it to 40% for that plastic trimmer and it still functions in our circuit, look at that. I almost cut the failure rate in half from the nominal recommendation. And so, and if I have different temperature variations and so on, I have to account for that. But it gives you the ability with one graph to say, oh, I need to pay attention to it, be more aggressive at derating or not, all in one graph. And so it allows us to very quickly Shwan, what do I mean by 50% derating? So let's say I use the example a few times, but let's say I have a circuit that has a 5-volt, 5 volts across the capacitor in this particular net on our circuit board. And if I pick a capacitor that's rated for 5 volts, it's at 100% of its rated value. If I pick a capacitor that's rated for 10 volts and I'm using it in a 5-volt application, it's at a 50% derating. It's being used at less than its rated value by a factor of 50%, by half of what it was. Okay, so it's a way that most of the tables talk about it, is that if our application's at some value, then the rated value needs to be some value higher to that, so that I get that ratio that it gives us, the, like in this case, 50%. So that's what I mean by it. And the tables we did were all normalized so that independent of the individual technology's actual failure rate, which you had to have other information for, and lots of suppliers provided fit rates, which was typically used. In other cases, we knew better and we used more appropriate failure rates for the application and temperature and so on. But it gives us a quick multiplier. If I use it closer to the rated value in this particular graph, everything increases their failure rate. If I use it less than the 50% derating, they improve their ability to do it. And like I said, in the notes associated with this, like for aluminum electric, you can see the line stops at 20%. It loses its functionality as a capacitor as it gets too derated, too much derating. If it's way bigger than what it needs to be, you lose some of the functionality or all of it eventually. So there's limits to how much you can derate stuff. And there's also financial and space concerns when you think about this. All right, one more curve, and this is a paper I did some years ago, is I said the derating curves that we used at Hewlett Packard were based on Mill Handbook 217. And any of you that have been in my presentations before, you know that I don't have much fondness for Mill Handbook 217. But what they did do is say, for the different stresses of, say, a capacitor for, say, temperature or voltage, they had equations that were based on field data, basically, and some experimentation, but mostly just field data. And they said the units that were derated for capacitance, say by 50%, tended to last longer. And then they created a formula for it, and they were published and available. And so what Dick Moss did is he used those formulas to create those graphics in the previous slide. Well, I said, we have better information these days for many, many components. There's physics of failure models, or there's life studies. There's information available to know how stress relates to the time to failure multiplier, which is similar to failure rate, but not quite the same. And what we did is then we said, well, let's say we're looking in this particular graphic. I had a paper that had a really nice model for 10 ohm capacitors for voltage derating, for voltage behavior with time. And it gave us a time to failure multiplier. And so if I was rating this at, I think it's about 84%, 83%, that's where the blue line and the horizontal line cross, is that we double the time to failure. So if we expected it to last for 10 years at a reasonable failure rate, if we derated to 83%, it was double that. Now we have a 10-year product instead of a 5-year product. And consequently, it also reduces the failure rate. And so I chose to use time to failure multiplier. I could have used a failure rate multiplier, which I think is more intuitive, at least for my way of thinking. But if I derated it to, say, 70% of the voltage rating, and you go up from 70%, it's almost 10x the multiplier for its time to failure multiplier. So its probability of failure is reduced because it has a 10 times the expected lifetime now. And so you can pick 1% or 0.5% or whatever particular node of failure you want, and you get an idea with that. Yeah, Ken, you're right. 10 ohms can burst into flames. Yeah. It's one of the notes that I remember, and it was do not use in clean rooms, as it's not always the way they fail, but they can. And so paying attention to their use and where they're used because of the way they fail. Electrolytic caps too. Um, they euphemistically call it venting, so that if they fail, and there's a couple of ways that they can do this, is they vent, which just means it explodes. That's what those little score lines on the top are for, the little crosshairs, is that's weakening the can in that area so that the explosion just goes straight through the top. Now, I don't know why. These things are all put in boxes, and that electrolytic solution, which is usually very corrosive, just goes everywhere. So if you're testing capacitors and you're expecting them to vent, um, make sure you have a face mask on or face shield on, or put them in an enclosed space where you don't get covered in electrolytic solution. But the idea is that we have the ability for our technologies, and in the literature and with some vendors, not all, we have physics of failure models, or we have life data models for particular specific failure mechanisms. And so for our application, we can tailor those models for our use, of the way we use those components, and create curves like this, or like the failure rate multiplier in the previous one, that are based on the better understanding, not just field data aggregated from all kinds of different applications, but for how that technology in a physics of failure kind of way behaves with different stresses. So it allows us to even refine our derating practices one step further. And this was a project I did, I don't know, it was what, 10 years ago? Not even, but it was about 10 years ago when I was working on it. And it's one of those that it does take some effort to get the models and so on, but it allows you to really tailor your derating in a much more accurate way for your application. So it's another way to think of derating. But I found curves, whether it's failure rate multiplier based on the derating guidelines themselves and map out those curves for different technologies, or using physics of failure models, is way superior for application and use within your organization than just a table, which give you point estimates or point recommendations. And my spell checker got the best of me. Is drawing working for in your organization? It should be derating for whatever reason. Sorry about that. And derating is it a factor in external stresses like vibration? Um, Not in the typical derating guidelines I've seen. In mechanical systems, you'll see it. It's not called derating; it's stress strength calculations. Um, they'll say you want a safety margin, or some other terminology. It's the same concept. If you know that you're getting external stresses like vibration, it's more paying attention to the assembly and to latching things down and making sure say like electrolytic capacitors are seated flush with the board or very close to the board, so they have minimal amount of vibration effect on their leads and on the joints. It's more of mechanical considerations when it comes to vibration of electronic components. And there are variations of that considerations in some designs. I know that the very high frequency, like the 5G and the more advanced telecommunication systems with very high speed signaling, is those systems actually cause some components to vibrate because they hit just the right frequency for that structure, and it vibrates, and it can break off components, and it can also, when designed improperly, it can actually start cracking the mounts to hold that box onto the cell tower. Just learned about this a couple of weeks ago. But the idea is that vibration is real and we need to account for it, but I haven't seen that in derating. The same concept applies, but I haven't seen it all that often. So look at that. I'm right about on time, so I'll stick around if there's any additional comments or questions. Thanks so much for participating. And as I think I have a guest speaker next month, and as usual, didn't do my homework to figure out what it was, but looking for it. Chris is on in 2 weeks. and should be another interesting and entertaining and informative presentation that he usually does. I think he's talking about why MTBF is bad. Let's see, I think I have the title of it here. Oh, he said why the MTBF sucks, and here's why. So if you in an organization that uses MTBF, you might want to take some notes on that one to help them break that bad habit. So I've seen a couple of thanks. You're all very welcome. Thanks for coming in. Thanks for participating. Let's see. Folks are spearing off to their next meeting. That's great.